So first of all, we'll discuss here what is the stiffness of the bolted member. We have member A, we have member B. In addition to this, we have the bolt and the nut arrangement. So when we say the stiffness of the bolted member, it means that we are interested to know what is the stiffness of the bolt. So we are interested in the stiffness of the bolt, and what we mean by member. Member means here this washer plus member A, member B and second washer. So when we say that it's a stiffness of members, you have to consider the two washer and two member A and B. Now as far as the stiffness is considered, if you are familiar with the spring force, we have spring force is given as the stiffness K multiplied by delta, whereas the delta is called as the deflection. So we have stiffness is defined as force divided by deflection delta. So first we'll discuss here some basic concept about the stiffness. For any member, we can represent the stiffness as force upon delta. Consider here a circular cross-sectional member of cross-section equal to A, length equal to L, subjected to the force equal to F and elastic modulus equal to E. We are very much familiar with the deformation here. Some deformation will take place of this member due to application of a force. So this member is get deformed to by certain length. Let that deformation will be equal to delta. So this deformation is takes place due to the force F, and we have deformation delta is given as force multiplied by L divided by area divided by Young modulus. So for the given member, we can represent the stiffness K, which is equal to force divided by delta is same as equal to A into E divided by L, where A represents the cross section area, E represents the Young modulus and L represents the length of the member. So this member we can represent with the help of a spring, and this spring has a stiffness K equal to F divided by delta. And for the given circular bar, we have stiffness is given as product of area multiplied by E divided by L, and this spring is subjected to a tensile force is equal to F. In addition to the stiffness of the bolt and the member, we'll discuss here few terms or get familiar with the few terms, that is a preload or is also called as pretension. Then the external loads is due to the tension, moment and the shear, and what is the meaning of grip and how to calculate the effective unthreaded length in the case of grip, that is in the case of bolt as shown in figure or in the case of a screw. Consider here we have a bolt and we have unthreaded portion and a threaded portion. This time we want to make a clamping of two member. So let's say we have member 1. So this one is representing the member 1 and we have second member. To generate here a clamping force, we'll use here nut which is snugly fitted and we apply a torque to the nut. Because of this, the nut will advance into the screw body, and since the nut will advance toward the screw body, it will develop a clamping force. So this one is the direction of a clamping force. So in this fashion, using the torque, we can generate here the clamping force. We can use here a washer also. So sometimes the washer is also used in between the bolt and the first member, as well as the nut and the second member. So this is the arrangement normally used in the tension joint. Now we want to make a certain term clear here. As far as the bolt and nut is considered, this total length here will be representing as capital LT, that is the length of the threaded portion. And the remaining one is the length of unthreaded portion, which is represented by lowercase ld. But when initially it is preloaded by applying a torque and generating a clamping force, then only that portion of the threaded part you have to consider which is inside the joint. The effective length of the threaded portion is only this much. That is, this one is same as equal to lowercase lt, and the remaining distance will be same as our ld value. So there is no change in the length of unthreaded But effectively we have threaded portion you have to consider only in the grip, not the total length. So make certain term very clear here. When we are considering the fastener, this total length is available for fastening, that is called as LT. LT is called as total length of threaded portion of a fastener. LD is the length of shank, that is a unthreaded portion. That is the length of unthreaded portion in the grip as well as without grip. And this portion here that you observed in the grip, so this total is called as grip here, is equal to LT, is the length of the threaded portion in the grip. So this term is more important rather than the total length here, because only the forces will be carried away by that portion of the threaded part which one is under the grip. So this portion you have to consider, not this entire portion. And we have total length L is same as equal to LT plus LD. Suppose here the cross-sectional area of the unthreaded portion is represented by AD, that we can calculate as pi by 4 DO square. And if AT represent here the area of the threaded portion, that you have to collect from table. Just now we have shown here that the stiffness K is given as force divided by the deflection equal to delta, that is deformation equal to delta, is equal to area multiplied by Young modulus divided by length L. So using this we can calculate the stiffness for threaded portion and unthreaded portion. The stiffness of a threaded portion will represent by K, which is representing the stiffness, and for threaded portion we'll use additional suffix equal to T, is given as area of the threaded portion, which one equal to AT multiplied by Young modulus. And whenever we have a grip is formed, we have to only take the LT portion, which is the threaded portion inside the grip. So this value is divided by LT, not by capital LT. And every time we can represent the stiffness by one spring. So we can represent here one spring, and we label this spring stiffness equal to KT. In the similar fashion, we can define here the stiffness of unthreaded portion, which is again represented by K. Suffix D is normally used for diameter of the unthreaded portion is same as nominal diameter. This time we have to take the area of the unthreaded portion equal to ED. Material is same, so we have same Young modulus divided by length of unthreaded portion, that equal to LD. Again this stiffness unthreaded portion by another spring. These two spring will be in series and is subjected to the same clamping force is equal to F. And whenever we have a two spring in series, we can calculate equivalent value as 1 divided by K equal to 1 divided by the stiffness of unthreaded portion plus we have stiffness of threaded portion, that equal to KT. Cross multiply and we can solve for K. So this one is representing the K, that is the stiffness of fastener equal to KD multiplied by KT divided by KD plus V of KT. And we can substitute from here and we can solve for it. So if you substitute and solve this equation, you will get the final value of the fastener stiffness, which I represent as KB, is equal to area of the unthreaded portion multiplied by area of the threaded portion multiplied by Young modulus divided by area of unthreaded portion multiplied by length of unthreaded portion plus area of threaded portion multiplied by length of the threaded portion under the grip, that is LT value. So two concepts we introduce here, one is the preload and one is the external load. We'll consider here an assembly which one is tightened by nut and bolt. Let we have a washer, then we have two material A and material B. We have one more washer at the bottom. So the top washer plus bottom washer plus two material A and B will give here one stiffness, that will be called as Km. So Km represents here the stiffness of material. So Km represent here the stiffness of material, which include the top washer plus bottom washer plus material A and material B. And let's say we have Kb is the stiffness of the bolt. So Kb represent here the stiffness of the bolt, which one is same as the stiffness of unthreaded part multiplied by stiffness of threaded part divided by the stiffness of unthreaded part plus we have stiffness of the threaded part. So initially you have to make the assembly of the material A, material B, washer and nut and the bolt. In that case you have to turn the nut so that it is snugly fitted the assembly and the assembly will get formed. Now hereafter the washer A, B and the washer will call it as two together as grip. So in this case the nut is get tightened by applying the torque is equal to T. As the nut is tightened by applying the torque, the nut will try to come closer to the bolt. Bolt will come in tension. So the tension force will show as a outward. This tension force formed by initial tightening is called as initial load Fi, and it's a tension. So whenever we have a tension force, you have to take the value as positive value. If you compare here the vertical distance between the bolt and nut, that has been decreased in the second figure. So you will find here that the grip length has been decreased by certain amount. So grip length here will decrease by an amount equal to delta m. Since the grip has been decreased in the length, the grip will come in compression. And the compression force you have to show inward. So you have to show here compression force. This compression force Fi is for grip and is the also initial load, but this value Fi is in compression. So whenever compression you have to treat as negative and whenever tension you have to treat it as positive. So the bolt is in tension, so the bolt length has been increased by an amount equal to delta B. And since the stiffness of the bolt is Kb, so we can write the value of Fi, which one is the tension value, has to be taken as positive value, is stiffness of the bolt multiplied by the deflection of the bolt, that equal to delta B. Whereas Fi is a compressive value. In the case of members, you have to take as a negative value and is given as Km, which one is equivalent stiffness for washer and two material and the bottom washer multiplied by the deflection of the material delta m. This time delta m is a negative value and delta v is positive value. So we have a initial load is Fi and this value is remains same for both, that is for bolt as well as material. So during the preload we have a deflection of the member is delta m and the deflection of bolt is delta v. Clearly from this figure we can observe here the value of delta m is not equal to delta b. Rather the value of delta m we have shown is a smaller value as compared to delta b because the value of Km, that is the stiffness of the material, is much larger as the stiffness of the bolt material. Why this is so? Because if you are familiar with the stiffness is given as a product of area multiplied by Young modulus divided by length of member. As far as the bolt is considered, we have a bolt of cross section area equal to DC, which one is much smaller as compared to the area of the material, and therefore the stiffness of the material Km is always greater than the stiffness of the bolt. So this information will going to plot a graph of force versus deflection equal to delta. This one is taken as positive deflection and this one is taken as negative deflection. So we have initial load is Fi, so we can show here the initial load is equal to Fi. Since the force is directly a function of delta, so we can represent the variation and we have the slope of this will be same as equal to Kb. And if you measure the deflection here from the origin up to this point, that will be the deflection of the bolt delta B, and the corresponding value will be equal to Fi, will be taken as a positive value. Since here the member is in compression and the force member is a compression force. So we'll represent here this law is equal to Km. And the value of the Km is greater than Kb. So you have to show the higher slope of the stiffness of material Km and lower slope for the stiffness of the bolt material. Here delta M is a smaller value as compared to delta B. So from origin we have to show the lower distance as compared to delta B, and you have to mark this point equal to delta M. Since it is already plotted on the negative axis, so you have to read this value as a negative value. So initially the load is Fi, which one is called as initial load. The bolt will come in tension and material will come in compression. Here the value of delta M we can write as the ratio of force to stiffness. So we have initial load is Fi and the initial stiffness of the gasket material equal to Km, and this total value of delta M is not equal to delta B, and we have delta B is again written as the initial load Fi divided by the stiffness of the bolt equal to Kb. Once it is preloaded, the structural component which is made up of the members and the bolt will start in operation. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.